I'm Sridhar Katragada. I work as a lead data scientist at the City of Virginia Beach. I'd like to introduce myself about my background a little bit so that you can have some context. So my background is in civil and geological engineering, and I started processing satellite imagery from 1992. So my journey went through different iterations of IT, and I'm currently working as the lead data scientist. So my passion is about space technology. A lot of you will be having that passion, I hope. And when I was in India as a at 15 years old, I was following the space shuttle launches on a shortwave radio, all the running commentary. And then a lot of that propagates into my background and life through profession as well. So here we're talking today about accelerate climate resilience with data science. So I provide you a general idea of what I'm going to talk today, project background and collaborations, past weather events, sensor network proliferation, national and regional data and models, the challenges we had, and then historical and real-time data assimilations and next steps and vision for the future. So the summary, usually you'll see three patterns in this. So having a geospatial background is one, and how data pipelines in data science can be done with a small footprint of people. So that you will see a lot in this, as well as sensorization and IoT and smart cities. So those are the three patterns you will see in my talk. So our city's cloud journey, it started with National Institute of Standards and Technology, and we participated in a Shark Tank-like pitch in 2016 and got some funding with City of Newport News, City of Norfolk, and City of Virginia Beach in collaboration with Virginia Institute of Marine Science. That was a 10-minute Shark Tank pitch we had to do. From that, we had funding for replicable smart city technologies. So when they said replicable, one thing I realized that in IT, in our infrastructure and on-prem, we could not replicate that easily. So that's how I started with cloud. And from that, I created a prototype in 2016 Christmas time, in the vacation time, and that we put in our AWS CTE on a cloud innovation challenge, and we won in 2017 and again in 2019. Both of those provided us $90,000 worth of credits to start off our AWS journey in 2017. And this project we used as part of our journey. So here, proliferation and aggregation of sensor networks. My background was in civil engineering and geological engineering, and I worked at US Geological Survey for 5 years in hydrology, as well as in NASA Stennis Space Center about SRTM data, shuttle radar topography mission data. So when I came to Virginia Beach in June 2010, I realized that there are very few sensors, only which were run by NOAA, 4 or 5 sensors in the city, in the region. So I thought the sensor network might be a key way for us to understand the surface water flow across the city and across the region. So that's how we started this project. And then the models were coming around that time in 2016, I think 2006 or 2016, the National Water Model came up. And then our Virginia Institute of Marine Science models also came around 2016. So then the big data processing is another big, huge task, and how do we do it in geospatial way? So Heavy AI is one of the companies is in US, and then formerly it was known as Omnisci, so we were using their platform to bring all that data together for visualizations. So this is a sensor network. So here you're seeing on the left side, we have, these are called StormSense sensor networks. This is out of our NIST as well as the city's funding. And these are autonomous sensors. You have an ultrasonic sensor at the left, which is hitting the water. And every 6 minutes, it sends the data to the cloud in AWS. And then it comes through Alexa. And citizens can ask Alexa, what is the water level at so-and-so bridge? And it tells you the water level in real time. On the right side, in our initial calibration phase, that's a USGS sensor from the federal agency. We have 10 of them for tide gauges, and we compared our data sets for calibration. So the two sensors, one is ultrasonic and one is radar. So we both use two different types of sensors. and both send the signal to the water. And we are currently also testing LiDAR. So this is our app on the right side. We have two different types of apps. Both are completely, you can use phones or mobile devices. They are not native apps, they are independent. And here is our workflow in Amazon. So we get the sensor data from different agencies, NOAA. We also get from USGS and also from our StormSense network. All our multi-cloud environments, we bring the data in. And on the right side, we use the API gateway for our front ends, what we have built there. And then Amazon S3 for data storage and Alexa for voice. And Amazon DynamoDB for real-time data. And we also use Amazon RDS for data collection. So this is on Windy map. So Windy you might have used on your phones for getting all the weather data. So here we provide the back-end data as well of all the different weather conditions from wind, from all the models, from ECMWF or any other model you can connect with. And also it shows the sensor levels. So now currently when you're seeing those 3 yellows, it's telling that it's going to be in the action stage of flooding. And it's in real-time 6-minute intervals. So this is a recent, so data science challenges are machines can learn a lot of things. And then also machines can do wrong things of the modeling of data when you're training them as well. So how do we understand and how do we do like a connection like mainly having a practical idea whether it's real or not? So that's a challenge for data scientists. To have all the historical data input and then try to predict for next 10 days, that's what we are trying to do here. So here what happened last 2 weeks, there was a rainfall event. The northern side of Virginia Beach is urban, and the southern side is rural, but it has a lot of bays, which is called like our Back Bay and Mackay Island Wildlife Refuges. Water comes through the sea here. So what happened in that last 2 weeks, we had a rise of water in the northern side from May 7th through May 14th, and it went down. And it was flooding around that time in Laskin Road area. And at the bottom, what you're seeing is at the same time, the southern area watersheds were completely going down in water. So you see, so what this provides us, you cannot measure with one value from a sensor to do machine learning. You have to have, here in our case, water level is one we can predict for 10 days using past 6 years, 7 years of data to learn by making the machines learn. And also we have to also look at precipitation on top of that, as well as wind direction and wind speed. So we are adding now all those to do our machine learning. So these are the national models we are looking at. So here there is a hourly predictions, short term, medium, and long term. So these are some of the data sets we are using for ingest to look at data sets. So 36-hour predictions is from Virginia Institute of Marine Science, my colleague here. So what we do here is we get 36 hours, 1 hour predictions at 5-meter resolutions. That's very high resolution of the flooding which has happened due to surge. And then citywide, we have a study called Sea Level Rise study. We have sea level rise scenarios as part of those rasters. And at the bottom, we have the sensor network. So we use a National Water Model Open Data Registry from AWS to take data, and here the exercise was in the past 25 years, and now they have past 42 years of data from National Water Model telling the stream flow and discharge every hour of the day. So the predictive data they provide as well as the historical data. So I was thinking that the historical data, it'll be useful for us to take several hurricane events and then bring that data down to 750 megabytes from the 157 gigabytes for the continental US. So these 750 megabytes is for 3,774 stream segments. So we used that and we looked at all those different hurricane scenarios, what has happened in the past, and then try to model that here. So here you're seeing a lot of hurricanes going through from 1850s and so on from NOAA data, all the different paths of the hurricanes within a 65-mile radius around the radius of our city. And here on the left side, you are seeing the North Atlantic Basin and the different events. and then also the category, the wind speeds, and then all the different types of storms and the names of the storms. And then this is the sensor network we are showing within the area, and it has all the different water levels and different wind speeds you can see. And here is the water from the National Water Model. What you can see is this is in Hurricane Matthew time, how the stream flow has occurred using the National Water Model within our area. And the stream flow we show with a big peak there, and that the peak is the highest peak when Matthew happened. That is the time when the city had the highest damage very recently in our city's history. And you can, this setup was done in Heavy AI. So this is a marketplace product from AWS, so which can consume large sets of data in gigabytes and then in millions and billions of records. And you can show instantly all the graphics so that you can make decisions. It also has a Jupyter notebook in the back end, so you can run your machine learning models as well and incorporate them. So this one you can draw a circle, and you can see all the stream flow different patterns, and also you can see on the right side, and you can do that in real time as well with the data coming in. So this is TideWatch map, and Derek will talk about that.
So this is a data product called the TideWatch Map. I work at the Virginia Institute of Marine Science at the College of William & Mary, and Sridhar and I have been working together for quite some time to talk about how we ingest these types of data. So this was the regional product that Sridhar talked about previously. It covers the entire Tidewater region of coastal Virginia, and it covers this at spatial resolution of 5 meter in the X and Y direction, of course in the vertical scale as to the accuracy of the LiDAR data embedded within it at approximately 6-inch intervals. So based on the data that we're able to actually ingest, we basically take data from the National Weather Service and NOAA. And the resources that kind of provides us is that we can kind of provide these hourly output rasters using ArcGIS Online and leveraging some of the AWS tools in our pipeline to essentially allow us to serve these raster tools out every 36 hours. And so these are hourly output products. So along the bottom of the screen, basically this gives you time series data for a variety of different locations at 6-minute intervals. We interpolate between those individual measurements, but it also geospatially gives you an hourly output raster that you can then explore and figure out specifically which areas in the state's coastal zone will be inundated on a regional scale. So at 5-meter resolution, each of these rasters are several gigabytes in size, and we kind of place these within a file geodatabase that allow individual localities like the city of Virginia Beach to be able to download and access those data. And if you can click to the next part, Sridhar, this will also allow them to kind of see the TideWatch data product. We ingest data from NOAA's water level sensors, along with the U.S. Geological Survey sensors, and city-owned sensors like those the city of Virginia Beach has installed through the StormSense project that was previously mentioned. So this is an example from earlier this month, I guess looking back over the last probably a little bit more than 30 days, but you can see there's been a significant amount of inundation that's happened just in the last couple of days due to heavy rainfall along with northeasterly winds in the parts of the city of Virginia Beach where this is shown. And so this allows us to ingest data from a variety of different sources, also allows us to look at our hydrodynamic modeling perspective by solving the physics shallow water equations, Navier-Stokes, and allows us to very quickly predict which locations are going to be tidally and storm surge inundated. Our next steps with this tool is, of course, also to integrate more accurate rainfall-driven inundation, since the city of Virginia Beach is particularly beleaguered by all 3 forms of inundation: tidal, rainfall, and storm surge. But for the real take-home value here, it provides model-derived property flood potentials hourly.
So the data provided by Virginia Institute of Marine Science, the hourly data, we can intersect with the properties and know in the storm surge time every hour how many properties are getting flooded. So here we started with the time series forecasting, which I talked about what we are trying to do. So here's the Amazon forecast we use, as well as Amazon SageMaker Studio Lab. So this is our data science, another data science employee who works with me. So she has produced these, and we worked together on the multivariate model first, and to see any univariate and multivariate model, how these things are we are going to be able to predict in the future. So here on the left side, you're seeing at the bottom the water levels. On the top, you're seeing the rainfall. And this is on the Elizabeth River, is one side on the west side of the city of Virginia Beach, where the water comes from the north. On the right side, the water comes from the south up towards the north. And this is where the Bay Area is. So here we did a 60% of the data from the last 1 year, and we are predicting on the 40%. So the prediction is in blue, and the 60% is in the orange color. And here we took the northern side and then the southern side, and then we did the analysis of both the areas. And then we used Facebook Prophet, which has the capability of fast driving time series data we can run through, as well as model with seasonality. So we wanted to see the seasonality and also yearly differences of the water levels as they move through. So in the visualization part, bringing together all this data and then being able to make the machines learn through Amazon as a separate entity. You can bring the data into the visualization platform, or you can run in the visualization platform using Jupyter Notebook and also provide the data in the interface. So finally, summarizing plant scenario simulations. So the way I think is the machines providing answers for human decision-making process, and also large-scale reanalysis data from NOVA, the analysis data which is coming in real time, as well as historical data, and also bringing the observational data, and also maximizing use of historical data to learn from, and providing flexibility to visualize answers to questions in real time for what may happen 10 days ahead. So that's what we're trying to accomplish through this process, and it might be within the next year we can be working on the real-time forecasting to be shown. Thank you. Any questions?
This is super cool, guys. I was wondering more about any of the newer IoT management services, if you've started experimenting with things in the AWS stack for that, you know, some of the new extensions of Greengrass and stuff. Are you guys looking at deploying additional sensors to build replication into the sensor net, or?
Yeah, sure. I think so. One of the things which I realized is nowadays LiDAR is popular and cars have LiDARs to see the distance. So we are using a LiDAR sensor. We tried with a LiDAR sensor on the water. And the LiDAR sensor, we wanted to do a secured communication. So there I was using Soracom, which is another AWS Marketplace product. So I used that at home by putting the LiDAR in a homemade equipment to test it out. And it works well with Clearwater. Then I was about to, so what the process there is, if our public works employees are driving around, they can take a sensor and put it in a lake, and 5 days later they can get it back, so they can have real-time data covered for engineers. So that was one of the thinking. And the other part of the question?
Sorry. No, it's okay. I was just wondering if you were doing anything with the IoT services specifically to replicate or supplement the existing external sensor nets in the region on top of StormSense. I know that there are a lot of researchers in that region that are trying to set up sensor nets. I was wondering how you were hybridizing those networks.
Exactly. So the way we did was, so initially we took the USGS's metadata format and use that metadata format for all the other sensor networks to communicate through the API like that. So our ingest goes through Lambda, and the Lambda converts it into that one single format where you're seeing estuary. So that's the USGS terminology we used. Then now we are having IntelliSense systems from DHS. So when they install, immediately we write that into our network, so it comes up in the same. So as soon as these networks, sometimes the Currituck County and the other county, they have similar sensors. Once they switch them on, it automatically shows up on the AWS as well as our maps.
Oh, thank you. Did you have any difficulty with refraction causing error with your LiDAR sensors?
Yeah, there are some issues that were referred to. So the sensor I was using was from, CERN, CERN, the collider in Europe. So their first innovation company was doing these sensors in LiDAR, and they have installed several in Europe. So it was, the size of the sensor is this small. It's like a little bigger than a quarter. And I used that, so I bought that, and I tested that. So, and I called them in the last 3 years, several times we had meetings with them to see how their sensors are behaving. So we are going to implement one in Virginia Beach and start making that one part, because that I can use a USB as a connector and then test it out in the field. So that's the LiDAR sensor we started using. Any other questions?
Hi, thank you very much for the talk. I was wondering, in your model that does the 10-day forecasting, is there a mechanism to do error correction if your model is off for?
Yeah.
And then how do you implement that using the AWS pipelines?
So currently the way we are thinking is, if we are doing a 7-year model, so we do the 10-day forecast on that model, and the flexibility of AWS, also the machine learning models, is you can think about monthly and the way, and we are looking at the footprint of the cost, what happens when you create the model, and it's very low cost for this model to be created. Once we deploy, we can continuously monitor it and then keep changing it, because one of the things in the model, what we are seeing is, because a lot of this predictive model data is coming through in real time and hourly segments, so we want to corroborate that and add that additional things to the model. But at the same time, we are realizing that the models which are predictive from the NOVA are different resolution scales, and how do we give our water level and our data science values back into the system for Virginia Institute of Marine Science, and as well as their model when they add precipitation to their model. So the pipeline is a little flexible for us, so initially, and then later on we can have a little more time series on it of how often we need to run the model. That's what we are planning now. I think in that lines. Did I answer your question?